Okay, let's get started. So, midterm 2, good, not good, awful. So I'm going to talk about them in a second, but I haven't finished grading them all. I promised to have them all done by Monday, so I'm giving myself a little break there. But I have like 30 done so far, and I'm very happy with what I've seen so far. Every single person that I've graded so far did better on midterm 2 than midterm 1. Every single person. And some people actually, the resulting grade, because I fixed midterm 1 at the same time if they do better, some people actually went up by 2 whole letter grades because of it. And everyone obviously did better so far, but I haven't graded everyone yet. Yeah.
But the cutoff staying the same?
Yeah. Yeah.
The average, how much better, like a lot?
It's the average, I'd say mid to high 60s%. Yeah. No. Yeah, mid to high 60%. The highest so far is a 188 out of 200 so far, and the average I would say is around 130, 140. So pretty good. Yeah.
Are the letter grades on Blackboard, like, did you change that to be accurate?
Yeah.
Okay.
Unless there are academic integrity violations, which there have been so far, but it's just if there are no more, I probably won't increase it, but you never know. Other questions about logistics stuff? Okay, so I'm just going to briefly talk about, I haven't uploaded these because there are some typos, as you'll see, but I'll have these uploaded by tomorrow. So the first one is true because regular operations are just union, concatenation, and star, and we showed the basic construction for grammars. You can do this with PDAs too, although no one did. So it's just, if you write basically these 3 things down, then you're all set for that question. Because those are just union, concat, and star. Symmetric difference is, but not many people got this one. It's precisely this. It's A intersect not B union, B intersect not A. So basically the strings that are in exactly one of A and B. If you just say that and the regular languages are closed into union, intersection, and complement, then you're all set for that. One person actually did say that the symmetric difference is exactly the same as what the DFA we built in EQ DFA, and that's perfectly fine too. I think maybe one person so far got part C, which is we're trying to see if an arbitrary Turing machine and an arbitrary DFA have the same language. Well, I can decide as an example E sub TM, because I can just feed in the input Turing machine, whatever was given to me, and a DFA that accepts nothing. And so if I can decide that, then for obvious reasons, now I can decide E sub TM. No, because you're working with a Turing machine and a DFA. Remember, Rice's theorem only works with single Turing machines. What's sorry?
Isn't like if you formalize it, if you have like if given a machine and a DFA with Turing machine, like they have the same.
Yeah, that's what I was saying. That this is not decidable, because as a counterexample, you can decide ETM. Yeah.
Can you give like example of regular TM?
Yeah. So you can do like regular TM as an example. Yeah. That'd be another example. Other questions? Okay. D. A lot of people did get this one, so I was happy. We can avoid step 5 because regular grammars have at most 2 characters on the right side, so we'll never have to break up long right-hand sides of roles. So we'll always have either 2, 1, or 0 things on the right-hand side, so we're okay there. I don't think anyone got part E. So I kind of outlined this, but I meant this one to be one of the harder questions and see if you were thinking about the pumping lemma. So the idea here is that if you have any string at all in the language that's long enough, i.e. at least the number of states in the DFA, then remember from the pumping lemma, we can pump this y part as many times as we like. Well, if we keep pumping up more and more and more, I'm going to get more and more strings, infinitely many, in fact. So if there is some string in the language that's long enough, then I must be able to have infinitely many strings in the language, because I can just keep pumping and get more. Well, if there's no string of that form, so this is kind of a quiz question, I think, where there's no string in the language of length at least the number of states, then all the strings in the language must be at most the number of states minus 1. But that means there are only finitely many strings in the DFA's language. So what we do here to figure out whether we're in one of the cases or the other is just we make a DFA once we know the number of states that has language all the strings of length at least that number of states. I make a separate DFA for that. And I can do that because the number of states in the original DFA was finite. So then I have this DFA, m sub greater than or equal to n. And then I just make the DFA for all the strings in the original DFA and have length at least the number of states. So then I just check, are there any strings that are in the language of m and have at least the number of states long in length? And then E sub DFA, which is decidable, can help us figure out whether which of the two cases it is. Either there is a string of length at least the number of states, or there isn't one. And that's all you need to do. Okay? So I meant that one to be a harder question, but it's to get you to think about the pumping lemma and the consequences of that, other than the fact that some languages are not regular. Any questions about that one? Yes.
For like a loop and accepting computation?
Yeah, so there is one person who got that. So one other technique you can try is if there is, you can just enumerate all paths up to, say, the number of states in length, and then you just see, is there any one of them that has a loop that ends in a final state, or has a final state after the loop from the start state? And then, therefore, you can say that the language is infinite from there. Yeah, so that's another way you can do it. Other questions? Okay, so I meant part F to be somewhat easy, but some people didn't get it, so I might as well just say this, that E sub PDA is equivalent to E sub CFG because we can convert back and forth between PDAs and CFGs. And so, therefore, it is decidable because we gave a proof that E sub CFG is decidable. Okay? And this, there's another reason why a reduction like this wouldn't work, but I'm not going to go into it. Part G is the quiz is a quiz question. If I just said the number of rules of type 1 and 2, then this would be false because we can actually figure that out. But I'm including the third type of rules as well. But just from the number of states of the PDA, I can't know anything about how many rules of the third type I'm going to make, because it depends on what the transitions actually are. If I have 0 transitions at all, then that means I'm going to make 0 more rules of the third type. But if I have a lot of transitions, even with the same number of states, I can make many more rules. So I can't know the exact number from just the number of states alone. Okay? So that was to get you to think about the 3 types of rules and the consequences for that. Yeah, a question? Okay, part H, there's another example. I have DCFLs here, but that was not required. One that some people gave, which was really good, was recognizable, which are closed under union and intersection, but not complement. So that'd be a counterexample to that. But another one you can just say immediately is that this is not a consequence of De Morgan's law. And so therefore, we can't infer anything from that. But a better answer would be to give a counterexample which is recognizable. Okay, any questions about the first whole question? Okay, second question. I was surprised very few people even put something on the question, let alone had an idea for. So this was basically one of the P-set questions. Actually, both of these, although the second one's a little more involved. The first one, all you do is you just say, I want all regexes in DFA such that the language of the regex is contained within the language of the DFA. A lot of people put that we solve this using EQ DFA, but all I want is that one is a subset of the other. I don't want them necessarily to be the same. That's the second question. And some people put the subset question on the second part, which they meant for the first one. But here, you just convert the regex to an NFA, NFA to DFA, and then you form the DFA here. We've seen this a few times, where I take the one that I'm given and the regex that I converted to a DFA, then intersect with the complement of the other one. Then if there is a string that the resulting DFA accepts, then that must mean that the DFA, the original DFA did not accept it, but the regex did, which means it's not actually a subset of the DFA's language. And then we just run E sub DFA on the resulting DFA. Second one is a little more involved, as I said. So here, we're not given D prime. So we have to check whether there is a DFA of fewer states that accepts these other strings as well. We're not given D prime. So how would you actually go forward with this? So I think one person did get this, which is good. What you do is you look at all possible DFAs of fewer states than the original one. Then the strings we need to accept are the original ones as well as the ones that we get from the finite set as well. And then we just run EQ DFA on every single one of those, on all those DFAs. If any of them say, yes, I accept that, that means it has fewer states and accepts the strings we want. Therefore, then we say accept. Otherwise, we've looked at every single possible DFA. Therefore, we reject. Okay? Does that one make sense? Yeah.
So my thinking of this was, I just thought, oh, you can't check the number of states in the machine because we did some language before the notes that had something like that, which was undecidable.
We can't check the number of states?
Yeah.
But it's written on the tape, for instance. You can just count the states.
Yeah, but you can't, like, there's something I remember from the notes that said something about.
Yeah, it must have been about Turing machines. Okay. About DFAs, it must have been something about the size of the language.
No, specifically the number of states in like a automaton. You can't do something like compare the number of states because you can't. It was like when you can't remove it and check the
the same. You mean the useless state one?
Something like that, I don't know.
But we can talk offline about that.
Sure.
Other questions about the second question? Okay, third question. I don't think anyone got this, which I was confused about. Is statement 1 correct or not?
Yeah.
Every finite language is regular. Yeah, because we can just make an NFA for each of the parts and then union all of them. Is the second statement correct? Yeah, because it has exactly one string in it. Third one, for fixed integers, alpha, beta, is this language regular? Yeah, because it's exactly one string. Are they closed under union? Some people said that they're not closed under union. They are closed under union. So, yeah. So step 5 must be wrong because it's the last one. Why is it wrong? No, it is a union. It's over some parameters, alpha and beta, such that either alpha is less than square root of beta or beta is less than square root of alpha.
Those languages are finite.
Each one is finite, so each one's regular, but the union of regular languages is regular.
Because there can be any number of alphas, any number.
And what does any number mean more formally? Infinite, right. So this is an infinite union of regular languages. We showed that it's closed under a finite number of unions, right? Because if you just think, well, 0 to the n, 1 to the n, I'm just going to union all the languages of the form 0 to the I, 1 to the I, just one string, for every single value of I. But then for that reason, I can show that every language is regular.
So it's basically saying a union of replacing alpha and beta with any number?
So if I just union over all alphas and betas such that one of those two conditions is true, and for that particular language, then that is the resulting language. But then that's just a union of finite, therefore regular languages. So then therefore the resulting language must be regular. But that's clearly not possible. So it's because it's an infinite number of unions. If it's a finite number of unions, that's definitely true.
I thought alpha and beta were fixed.
Does alpha and beta say fixed in the fifth step?
Well, I mean, I thought there were a sequence of arguments and each one built on.
Yeah. Yeah, but it doesn't say alpha, beta fixed in the fifth part.
But
It seems like that's implied.
yeah, I don't think so too. That's probably why there's confusion.
It's basically the same.
I'll look at that again.
Okay.
Yeah. Maybe I should quantify here that alpha and beta are at least 0. But I'll look at that again. Maybe I'll give some points for that. Yeah, that should be quantified there. Other questions about that first part? Yeah.
You could also, like, the way I thought about it, like, split it up and do the first part and union the second part.
Yeah, that's possible.
And then you can really see that it's, if you don't think they're fixed. then-
Yeah, but that's a fallacious argument because if you have two non-regular languages, their union may not be non-regular.
Repeat that again.
If you have two non-regular languages, their union could be regular,
Okay.
right? Because if you take a non-regular language and its complement, their union is sigma star.
Okay.
So that doesn't necessarily work. It will work. Oh no, it won't work in that case. Yeah, that argument won't work. You can assume that if you assume some other things, you can say something like that, but not in general. Other questions? Okay, so why is this not regular? So one of the biggest problems I'm seeing so far is that people are not picking a string that's in the language and long enough. So if some people pick something like 0, 1, 1, 1, 1, that's not necessarily long enough, even though it's in the language. And then some people pick 0 to the p, 1 to the p, but that's not in the language at all, because the number of ones it doesn't fit one of the two conditions here. So pick a string that's in the language and long enough. Then you can move forward. From there, you just look at all possible decompositions, but since we're in the regular case, then the x and y parts must only be in the zeros. So some people had trouble in saying that, okay, the y part can hit the ones as well. But since we guarantee that the first p characters are zeros, then I'll never have that issue. So all possible decompositions look like this. Well, then if we pump up, then we get this string, pump up to I equals 2, we get that string. Then all you need to do is check the two cases, whether or not either of them is satisfied. So the first one is not satisfied because if you look at the condition itself, which is p plus b less than that square root, then we see that that's not true because the square of the left side is larger than the right side, than the thing in the square root of the right side. And then we gotta check the other condition because any condition can still have us be in the language. So we need to check all conditions, which is both of these here. But then obviously that this is not true because square root of 2p cannot be greater than p squared plus 1. So therefore, the resulting string cannot be in the language. And so it's not regular. Other questions? Yeah.
You know that it's in the 0 because xy is less than or equal to p.
Right, yeah. Yeah, so that's why we usually just put the first p characters as some particular run of zeros or something. So therefore, all the decompositions look the same.
I thought that there was an example where even if p was the first character was p times it could still be in the second.
That's for context-free languages.
Okay.
For regular, it's always within the first p characters.
Okay. All right.
Other questions? Yeah.
Would you mind explaining why 0 to p and 1 to p squared plus 1 is in the language 0 to p?
Yeah, so look at this string. then all we just need to check is alpha, the number of zeros at the beginning, less than the square root of the number of ones, or the other way around. So is it the case that p is strictly less than square root of p squared plus 1? Yeah, of course, because this is at least p, and therefore you're also... Actually, it's strictly more, because the plus 1 will get you over the p there. Strictly more, yeah.
Rather than taking the roots or something, can you just pick 0 to the p minus 1 and 1 to the p?
But that's not necessarily in the language. So if I look at 0 to the p minus 1, 1 to the p, how is that in the language?
I mean, if p is suppose the root of beta, and one condition is that beta is the...
Well, no, alpha is the number of zeros at the beginning, beta is the number of ones at the end. And so it must be, so this would imply that p minus 1 for the first condition is less than the square root of p, which is not true in general. Other questions? Yeah.
What about the other OR case with p less than square root of n?
Yeah, so I checked that here, but a string you could have picked is just flip the 2 exponents. So that would be another string that works.
How do you pick 2 different...
Yeah, either of these will work.
How does it work with the top one?
Because that's the proof here, where you just put in another beta zeros, and then the proof is that this cannot possibly hold, the p plus b less than that. And then the other condition is pretty much obviously false, so that this cannot possibly happen, p squared being less than the square root of p, pretty much.
Oh, so you don't just like flip the square root between p and p squared plus 1 to prove it? You have to add...
No, is beta less than the square root of alpha?
Yeah. So
The number of ones less than the square root of the number of zeros. So one of them, for either of these strings, is going to be nonsensical. But it's the other one that it needs to be shown.
oh, because it's OR.
Yeah, or. If you put and, this language is empty. But or, it's non-regular. Yeah.
So regarding that or, when you pick that W and it only works for the first case, why is it that you don't have to pick another W for the other case?
No, it still fails the second case.
Yeah, I understand that. So then do you not even need to look at the
No,
second
I need to pick exactly one string
Yeah,
to look at every possible case.
okay.
Any possible chance that this string could still be in the language. I need to look at every possible way.
Do you look at the 0 to the p squared plus 1, 1 to the p in that in your...
No. The proof can be done in 2 different ways.
Okay.
I'm just mentioning another string that could work. But you still pick one string.
Yeah.
Either one will work. Then. Other questions? Okay. So the first 3 questions were not as well done, but the last 3 were very well done. I was very happy about that. So most of you probably know what to do on these ones, but I'm just going to go over them anyway. For all strings that start with a 0 and end with a 1, that's pretty easy. Pretty much everyone got that one. Convert it to an NFA. It doesn't say that you have to use the methods in class. So if you didn't use the methods in class and happen to have an NFA that works, I gave full points on that. So, but this is the one from the methods in class. So it's just 0 at the beginning, any number of zeros and ones in the middle, 1 at the end. And then the NFA to DFA is pretty simple. It's pretty much just the p set one, just smaller. Question 5, nearly everyone got full points or almost full points on this one. So some people erroneously put for step 2, they put epsilon up here, but is S nullable? No, M is nullable for sure, but S we can't find out whether it's nullable or not because it's not full of nullable variables on the right side for any role. So in fact, you shouldn't put or epsilon for S0 there. So I took a few off there, but pretty much everything else was pretty straightforward. And part B was also very well done as well. It's just a straight copy of the rules to form the loops. For the two rules up here, you could put them as self-loops as I mentioned, or you could have loops coming out. Either way is okay. Any questions on question 4 and 5? Okay, so those were pretty easy. Question 6 was also very well done so far. You just make the 1, 0, 1, and then just direct all the other transitions appropriately. And then converting, you can rip the states in any order, and I observe it all the way through. So this is just one particular way. I just rip out 3, 2, 1, 0 in that order. So this one should be very well done as well. Any questions about the entire test? Yeah.
For the previous question, the one before that, actually. Yeah.
Yeah.
Question 5, I think.
Question 5?
Yeah, part A.
Mm-hmm.
For step 1, we have to make a new start variable.
Yes.
Because there's an S in.
On the right side of a non-start variable.
Okay, so it can be in any row.
Yeah, the order of rules doesn't matter. I said that S is the start variable.
Yeah. I guess I was thinking that you didn't need to replace the start variable if it wasn't in the row with that variable. So because we started with S and it didn't have an S on the right-hand side of that row, you don't need to replace it.
You need to replace it if it's on the right-hand side of any rule. Any rule at all, yes. Yep. Other questions? Okay, so let's go back to this. So I re-looked at the deterministic context-free language stuff, and you guys were very correct in pointing out that this is not actually a DPDA. So remember, this is the 0 to the n, 1 to the n PDA that we've talked about several times now. But this is not a DPDA because if we look at these two transitions as an example, then if I have a 0 on the input and a 0 on the stack, both of these transitions can be applied. So therefore, it's not deterministic. So, but you can fix it. How would I fix this? Well, what we're going to do to fix it, so I'll just go back to red here, is we're going to have epsilon be accepted by the start, or have epsilon be accepted by the start state right at the beginning. So I'm going to make the start state an accepting state. But to fix this, I'm going to change this transition to be a, actually it doesn't really matter. I'll just put a 1 epsilon epsilon. And so the empty string is exactly one thing it could ever do. And if you have any non-empty string, then you can either stay in that second state or go down to the other state. There's no choice there. Okay, so therefore this is a DPDA now. If there are other but in the other case, if we have like a 0 here, then we direct that to the empty set as I mentioned before. So if we have an unwanted combination, then we just direct that to go to the empty set.
That 1 epsilon, would that be of 1 when they put out copy 0 on the stack?
Oh, good point. Yeah, that should be you're absolutely right. Yep. So that should be a 0. That's not for the DPDA reason, it's for the language reason. To actually get the right language at the end. So, but you're absolutely right. Other questions? Yeah.
When you have the part of that epsilon there,
Yeah.
transition, I thought that if you had a 0 and then epsilon, that it could
take either one. Right.
Oh, it could take either one.
Yeah. So that's why I said it was not a DPDA.
Okay.
So in what we have in red here is the fix that gets it to become a DPDA. So now if I have a 0 or 1, if I have a 0, I have exactly one transition to do, and 1, I have exactly one transition to do. So I'm all set.
So like, talking about epsilons last time, we said that the epsilon was like kind of a container we could think of, or
Yeah.
but
So
it doesn't seem like it is that
right,
way.
right. So way you can think about it is if we have a double epsilon at the beginning, like don't read, don't pop, then there can only be exactly one of those transitions. Because if you have any other transition, then that is compatible with the double epsilon one as well. So so you were right to point that out last time. I was wrong. Yeah.
So the DPDAs not need every state drawn out as possible? Like
Correct. Yeah. Or every transition. Yeah.
So I really understood completely what you're saying finally at the end, but now it sounds like it's wrong. Is that so? You're not picking one of the 4 for every pairing.
No, you're still picking. You're making the transitions defined or not defined. So if you look at, say for this state right here, if you look at input 0 and anything on the stack, there's exactly one transition defined for any of those possibilities. If you look at 1 with anything, there's one transition if you happen to have a 0. But if you have a $sign on top of the stack with a 1 on the input, right, then we need to direct that to, and whatever here, to go to empty. Because that's an unwanted combination. So there's exactly one transition defined for every pair.
So is that preference of the order of?
No, that's an incorrect reasoning. So as I was mentioning here, if we have a double epsilon at the beginning and whatever for push, then there can't be any other transition here, right? So if I happen to have some other transition like 0, x or something, I can't have both of those transitions simultaneously. Right, exactly. Yeah. So I was completely wrong last time. Yeah.
Can you explain why the fix you made in red for read 1 pop 0 doesn't change the language?
Right, because the only issue is that we don't accept the empty string now. Right? We had the epsilon on that vertical transition because we needed to go all the way through with the empty string. But here I fixed that by making the start state an accepting state. So we get the empty string there. That's the only reason for it.
Doesn't that mess up the other non-empty strings?
No, because that means if I'm going to accept, then I have a 0, 1 at least. Right? I can't have anything else for a long. So that means I go one transition on the top, and then I read the one going down. Yeah. Other questions? Yeah.
If you have a state, for example, and you have a 1 epsilon and then a 1, 0, and you have both of those come
No.
in the state?
No.
Okay.
Because they're both, if you have a 1 on the input, 0 on the stack, you can do either one of them.
Okay. Got it.
But if you had 1 with anything else other than 0, then there's exactly one thing you can do. But it has to be true for every pair. Yeah, so I was wrong last time. I make mistakes. So you were right to point them out. Other questions? So let's talk a little bit more about DCFLs for the rest of the first half, and then we'll get into some really cool stuff in the second half. In my opinion, cool stuff. All right, so what we just shown, essentially, is that 0 to the n, 1 to the n is a DCFL, because I just made a DPDA for it. What if I did this instead? So if I had 0 to the n, 1 to the n, but now 2 to the m, where for any m, n and m, at least 0. Can you say anything about whether that's a DCFL or not? Actually, this is a DCFL. Why? Here's the idea. The 0 to the n, 1 to the n, we know how to handle using the DPDA up here. So over here in this state, the accepting state at the end, we just read, or actually in the other one too, we just spit off the 2's at the beginning, right? So if we, at the end I mean, so if we just read off the 2's, I can remember the number of 2's has nothing to do with the number of 1's or 0's here. So in fact, I can just spin off 2's at the end. And that's deterministic, because if I go over to there and I see a 2, oh, well, I better see a 2. If I see anything else, then I should go to the empty set, the reject state. So this is in fact a DCFL as well. What about flip the role of 0 and 2 here? So I have a different number of zeros possibly than the number of 1s and 2s. I think that's right, yeah. Yeah, it seems like a DCFL as well. Just spin off the number of zeros, whatever they are at the beginning, and then just change the role of 0 and 1 to be 1 and 2 here. So in fact, this is a DCFL also. Call these last two to be L1 and L2. What is L1 intersect L2? 0 to the n, 1 to the n, 2 to the n. Is this a DCFL? No, because it's not even a CFL, so therefore it can't be a DCFL. So what does this tell you about DCFLs? They're not closed under intersection. So DCFLs not closed under intersection. Okay, any questions why that's true? Mm-hmm.
Because they can't all be equal, is what you're saying? The n values, is that what you're
What we're saying is that this language is not even a context-free language, so there's no way it could be a deterministic one. But we started out with two deterministic context-free languages. So therefore, their intersection is not context-free. So therefore, it can't always be the case that their intersection is deterministic context-free also. Yeah. Yes, because remember, it's just a PDA with some special characteristics. Right, so this, we haven't shown it quite yet. So if I show eventually that DCFLs are closed under complement, they are closed under complement, what would that show about DCFLs and CFLs? They can't be the same because CFLs are not closed under complement, but DCFLs are. So, well, what would that imply? Well, what about 0 to the n, 1 to the n, 2 to the n complement? If DCFLs are closed into complement, which we haven't shown yet, yeah. Well, I look at every single integer n at least 0, and I look at the strings n0s, n1s, n2s, put that string in. Yeah. Yeah, so the n and m are arbitrary and not related to each other.
Yeah, but in the L1 there can be a case where n is equal to m is equal to n, right?
The number of zeros and ones here is exactly the same.
Yes, but so will be the case in the...
Yeah. I just stick on any number of 2's that you want at the end for L1's case.
Yes. So is that the same case here? Is it? In the
Which case?
0 is to n, 1 is to
Here it's
number of zeros and ones, and we can just spin off.
this is a potentially different number of zeros and ones and 2's.
Yeah.
This one is the same number all across. Other questions? Cool. So what about this language? Could it be a DCFL? Yeah. Yeah, it's the complement of DCFL. If DCFLs are closed into complement. No, if it were, what would the complement of this be? It would also be a DCFL, but we just showed it wasn't. So if we show DCFLs are closed into complement, this is not a DCFL, but is a CFL. So in fact, we have a language, potentially, that is a context-free language, but is not deterministic context-free. Like an explicit example. Right, yeah. So if I show they're close in a complement, then this complement version cannot possibly be a DCFL. But we showed before that it actually is a context-free language to show that CFLs are not close in a complement. Other questions? Okay, so how would we actually show that DCFLs are close in a complement? Well, I kind of outlined it last time, but I want to go a little bit more detail this time. So how do we show that DFAs are closed in a complement? The languages of DFAs are closed in a complement. The switch the role of the final and non-final states. What would be the issue here? Well, we have these epsilon transitions, which seem like an issue. Could I have a situation where one computation ends in an accept state and another one ends in a non-accept state for a deterministic PDA? Could I have something like this? No, why not? Right, because there's exactly one transition I ever do. So there's exactly one computation that I ever do. Actually, that's not true. There's at most one computation that I can do. Could there be 0 computations in a deterministic PDA? Meaning, I don't read all of the input. Pop an empty stack. So one thing that might happen is pop an empty stack. How did we fix that for DPDA? The special character at the beginning, and if we ever have a situation where we have a pop on a transition, we have another one that corresponds to popping that special character and then going to the empty set state where we just read all of the input anyway, even though we'll never accept. So in fact, we will always read the input. Yeah. I'm not sure what the question is. Well, it depends where the transition goes. Well, if it goes to a non-accept state and you take that transition, then you're not going to accept there.
Okay, so like on the transition, there's you pop it back on that transition.
Mm-hmm.
And then
So if you're in a final state, then you take a transition where you pop a character off the stack and the stack was empty, and so therefore you stop. No, that's not a computation because the machine didn't actually stop. It stopped because of a premature reason. No, it would not accept the string because it's not a full computation in that case. Other question, yeah?
Can you have that sort of black hole state after you pop an empty stack and you fix that by having this transition where you consume the rest of the input?
Right.
Can that state be a final, like an accepting state?
No, it's never a final state. Yeah, it's a dead state in some sense. Other questions? Cool. So we fixed this last time, and what we found is that we can fix any DPDA to always read all its input. Because if we stop prematurely, that means because since there's exactly one transition we ever do, then we fix that by we always consume the input even if we go to empty set state to consume the rest of the input. What could be another issue that would, if we can't just flip the states as to whether they're final or not? We have exactly one computation that we do now because we read the input. So we can't fall into this issue right here where we have one that goes to accept, one that doesn't. But what could happen? What could happen is we're going in this one computation. We end in an accept state. On the way we go to an accept state, we've read all the input at this point. Then we take an epsilon transition, and let's say it doesn't matter what the pop is, and it doesn't matter what the push is. And then that transition goes to a non-final state. Well, if I flip the final and non-final states, do I still accept the string? Or is there a way to still accept the string? Yeah, because I must do exactly the same computation because there's exactly one to do, since all I did was flip the states, then what would happen is I would go to a non-final state. This transition's still here, but I have an accept state over here, which means I can still take that transition and go to the final state anyway, which means I'll still accept the string even though I want the complement of the string, of the language. And so this is undesired behavior. So how are we going to fix this? I still want to flip the states as to whether they're final or not, but how do we fix that? Well, I got to have epsilon transitions because I can't always just pop or push on the stack. And I can't just keep changing the stack one by one. I could have a transition that just never touches the stack. So we got to think about this a little more. Well, let's see. The way we're going to do it is we're going to have a copy of every state that is an accepting state, an accepting version of that state. And what we're going to do is, as long as, if you ever enter an accept state, then if you're going to keep reading epsilon transitions, you better stay in an accept state, right? As long as you're reading, having epsilon transitions, you better not leave a final state to go to a non-final state, which would fix that issue that we just have. So how do we actually do that? So for any state Q, looks like an A, add a new corresponding final state. I'm going to call it Q sub A. So even if Q was final before, it's still final now, but I have a final version of it, another version of it as well. If it was non-final before, I have another copy of that state that is accepting. Yeah.
Is this in the one before we flip it or after we flip them all?
Before we haven't flipped yet. Okay. We got to make this modification, then we can flip.
Okay.
Yeah. So what do? Well, let's see. So if we have a situation like this, where we have delta of the state that we were in, and we do read and we do pop, and we go to some state R and Y. So we go to state R and we push Y on. Well, we have 4 states to deal with now. Q and R, obviously, but now Q sub A and R sub A because I have those transitions now, those new states now. So let's look at those states. So remember, so Q and R could be accept states as well. I'm not saying that they're not. I'm just saying that Q sub A and R sub A are accept states. Well, this is what is called a reading transition because we really are doing a read on this transition. So in all reading transitions, we're just going to go back to the original state that we were supposed to go to in all cases. So here, I'm not going to delete the original transition, which was AXY. I'm not going to delete that transition. But if I was in Q sub A before, I'm going to add a transition to R because I want to go back to the original, what the DPDA was supposed to do. And since this is a reading transition, it's okay for the DPDA to go from an accept state to a non-accept state potentially. That's okay. It's the only issue is when we have an epsilon transition that can cause us some issues. So here I'm still going to put AXY. So the only other issue is that the transition is not reading. It has, instead of an A on it, it has an epsilon on it. So let's look at that situation. So this will break, I'm telling you right now, this is going to break down into 2 parts. We're going to have to handle 2 different situations. Well, it says Q, not reading anything, whatever it does with the sec, goes to state R. If Q is a final state, it actually is a final state, should we go to a final state on the right side? Because it's an epsilon transition. Yeah, because we want to stay in an accept state as long as we're seeing epsilon transitions. So in this situation, so here and Q final, it actually is a final state. I'm not going to draw it that way, but Q is a final state. Q sub A down here, R sub A over here. So then we got to handle what Q and Q sub A would have done. Well, Q itself needs to go to a final state no matter what. I don't know whether R is a final state or not, but I know R sub A is a final state. So I'm going to go down to R sub A because I guarantee it's a final state. If the original R was a final state, this doesn't change anything. I'm still going to simulate the machine in the same way in the accept versions of the states. So here the transition looks like this, and then the Q sub A version, well, I still got to go to an accept state because Q sub A is a final state. So I'm going to go to R sub A. And then what's the only other possible case? We have this epsilon transition, and what about Q? It is not final. Okay, so let's look at that case. So I'm just going to copy this down. And then I'm going to put this in red, not final. Let's reason about the Q sub A transition. Does it still go to R sub A? Yes, because it's an epsilon transition, so it needs to stay in an accept state. R sub A is a perfectly good one. Well, Q is not final, so should it go to an accept state? No, because if it's not final and an epsilon transition takes it to a final state, then that's precisely the thing that we're trying to avoid. But I'm trying to simulate what the original machine would have done. So let's see. So then we are going to have it go directly to R instead. Okay, does that make sense? So all we're trying to do is avoid the issue of where we have an epsilon transition that takes us from either from a non-final state to a final state or a final state to a non-final state. Yeah.
You copy the new set of states, you add the transitions as well?
I copy the states, then I add all these transitions that look like this.
Okay, so before you do that, there's no transitions?
No defined ones, yeah. Yeah, so, but as you can see, these mimic the original machine almost exactly, because it's like parallel copied over. But when I just make the states, I don't add any transitions yet, then I add these ones, which it emulates the machine. Other questions? Okay, well, let's see. What does the situation look like now? Well, maybe we're just in this computation, and then we do some transitions, and then, oh boy, we enter a final state now. Okay? And then, let's see. Then we may go down to the A-level states, and then we're going to maybe read some more epsilon transitions as an example. And then finally, at some point, we are going to read some character, which means what? Are we going to stay in the A states or go back up to the original state? We're going to go back up because, remember, if we have an actual reading transition, we're going to go back up to the top no matter what, the original state. So that means that maybe this is an actual read transition, we guarantee. The state we end in may or may not be final. That's depending on how the DPDA works. So what we're going to designate as a reading state, although that's not technically correct yet, is this state. So this is a reading state. Okay? But this is not quite correct yet. We're almost there. We're very, very close. Okay, so what could the potential issue be? Well, one potential issue is that we have some transitions out of some state on this left that actually do a read, and then they go to some state, it doesn't really matter. And then maybe another transition that reads something. And then another transition that does not read, but it has to pop something else. Could this transition pop an X, the one that doesn't read? No, because the other two transitions are compatible with that transition. And so therefore I have two choices. That makes it non-deterministic. So that can't happen. But I could have something else that's popped. That's okay, because if you just look at the definition, if I have a Y on the stack, I have exactly one transition to do. If I have an X on the stack, it depends on what the input is. If it's an A, I still have one transition. If it's a B, one transition. So this is not a reading, this state over here, this is not a reading state because some of its transitions read and some of them don't. Okay? So how would we fix this? Well, here's what we're going to do. Once I remember what we do. All right, so let's look at this situation. Well, what we're going to do is look at all the transitions that actually do read something, and then we're going to break them up. We're going to and tear their hearts open. We're going to break up the transition first by not reading, doing whatever the pop is on that transition. Then after that, do the actual read. Then the new state we're going to add definitely only reads. And so then we can call it a reading state. So let's just look at a situation like this. So we have a state Q, and say R is over here, S is over here. And then let's just copy those two transitions. Whatever is pushed doesn't actually matter here. But what we're going to fix here is that we're going to add a new state in the middle. So we're going to still have states Q, R, and S over here. But we're going to add a new state called Q sub X. And the key is we're going to do this for, I call, semi-compatible transitions, a term that I just made up just now. But a semi-compatible transition is one where it does read something and the pops are the same. So note on these two transitions, they pop the same thing. This will not work if they pop different things. But we will handle this for anything that you could pop. So these two transitions are semi-compatible. So we're going to do it this way. So we're not going to read on this first transition, the Q sub X. We are going to pop on this transition the character that was the same on both of the original transitions. And then we're not going to push, because the pushes could be different. But over here, in Q sub X, we're going to emulate the same transitions that the original one did. So here we're going to do A, but not pop here, and then push Y over here, read the B as we're supposed to, epsilon, and this is supposed to push a Z. So note, Q sub X now has every single transition coming out of it being a reading transition. So now we can call Q sub X a reading state. So now Q sub X is a reading state. Okay, so how do we actually do the flipping of the states now? So now, finally, to get the complement, turn all non-final reading states into final states, and vice versa. So we're only doing this on the reading states, not every other state, but only on the reading states because we want to have it such that the end of the reading transition be different, obey the complement operation. So by doing this, we guarantee that we actually get the complement because we avoid this issue of a final state going to a non-final state on an epsilon transition. Semi-convoluted, but if you go through the details, it's actually pretty simple in how it works. So just to recap, and we'll have a break. The issue we had was that we do have a single computation. We fixed the DPDA such that it always reads the input, so that's good. But we have this issue where we have this incompatibility in terms of transitions where I have an epsilon transition that changes whether a state is final or not. So if I just flip the final states and non-final states, I still will accept the string. So what we thought of was, let's have an accepting version of every single state, and then for all the possible transitions we could see, let's mirror the original DPDA by either going down to the accept state or coming back up or something like that. And then we had to look at epsilon transitions based on whether the original state was final or not. Then we noted any state that has an actual reading transition coming out of it is a reading state. But then we have an issue of whether some transitions read, some don't, but then we can easily fix those. And so finally, we can convert the reading states to final and non-final, and then we get the complement. Any questions about that? So I'll never, ever ask you to, unlike the final or something, to emulate something like this, but the important upshot of this is that DCFLs are closed into complement. That's the important takeaway message, yeah.
So just to be clear, the reason why you, that example of the
Yeah.
The reason why that's bad is because epsilon is also
Right, because we have a transition that some that read, some don't. That's the only issue that we have. And then we fix that by making a new state that definitely only reads going out of it. So therefore it's a reading state. And then we could just flip from there. Other questions? Oh, and a quick note, Q sub x should have the same parity as whether it's final or not as Q does. Just a minor note, but yeah. It should be Q sub x because it's in between Q and the states that it ends up at. Other questions? I think it's right time for a break.